Imagine walking into your classroom and heading straight for your favorite seat. It has your name on it, at least in your mind. But someone stronger claims that spot, booting you into the aisle. Or imagine you and a friend are sitting next to the wrong lab partners. To fix it, you mutually trade seats to form better pairs. Down at the microscopic level, atoms and elements behave exactly like this. You don't need to memorize a bunch of complicated math to understand chemistry. You really only need to track which elements are strong enough to take whose seat in a molecule. Let's look at that first scenario, the strong kid effect. For this, our tough kid is iron, and the kid currently sitting in the seat is an element called copper, which is bonded to sulfate. When copper and sulfate are joined together, they form a bright, vibrant blue liquid. Watch what happens when we take an ordinary iron nail and drop it directly into that blue liquid. Iron is a highly reactive element. It prefers being bonded to the sulfate, so it bullies the copper out of the way and takes its place. You can see the evidence of this takeover right in the glass. Over time, that vibrant blue color starts to drain away, fading into a pale, nearly clear liquid as the iron claims the sulfate. The displaced copper has to go somewhere. Since it got kicked out of the liquid, it ends up clinging tightly to the iron nail, coating it in a thick, muddy brown layer. Because one stronger element forced a weaker one out of its bond, we call this a single displacement reaction. Now let's observe the partner swap. Here we have two different pairs of bonded elements, sodium sulfate and barium chloride. Sitting in their own separate containers, both of these are perfectly clear liquids. They look exactly like drinking water. But pour these two liquids into the very same container, and the atomic partners realize they are mismatched. They immediately agree to a trade. The sodium breaks off to bond with the chloride, while the barium swaps over to bond with the sulfate. The result is instant. The moment the clear liquids touch, they create a heavy, chalky white solid that drops rapidly to the bottom. That brand new solid resting at the bottom of the beaker is known as a precipitate. Because two pairs of elements mutually traded partners to create this solid, we call it a double displacement reaction. Those are the two reliable rules. Single displacement happens when one strong element takes a spot, and double displacement happens when two pairs trade spots. You can put this exact logic to work in your own kitchen the next time you need to clean blackened, severely tarnished silverware. All you need to do is place the tarnished silver into a pot of hot water, a spoonful of baking soda, and a crumpled sheet of aluminum foil. In the hot water, the aluminum steps in as the stronger kid. It rips the sulfur, the black tarnish, right off the silver, claiming it for itself. Your silver is left perfectly clean and shiny. Chemistry is happening all around us, operating as a predictable, endless game of atomic musical chairs.